today we're going to be solving this question where we have to just complete the molecular orbital diagram for the pi bonds in the hepta-2,5-diene 3-eel anion, and it's basically incomplete, so we have to like complete it, and we have to first start by like just plugging in this lone pair over here so as to satisfy the negative charge over here that we see, right? And other than that, now let's start with the main question, which asks us for the number of, so this CP, that refers to the number of atomic p orbitals that are involved in the pi system. So for atomic p orbitals, the formula is basically that we have to multiply the number of pi bonds. So we have like this pi bond over here and another pi bond which is over here. So 2 pi bonds, so 2 into number of pi bonds. So already we have like 4 p atomic orbitals plus number of atoms with lone pairs in unhybridized, bold the unhybridized, okay? So plus number of atoms with lone pairs in unhybridized p orbitals that participate in resonance, which would be just this lone pair over here, right? So in the middle. So that is one lone pair plus the other 4. So basically this lone pair is a part of an sp2 hybridized, right? It's part of an sp2. It is participating in resonance, right? So it is not a part of that, right? It is just like in an unhybridized p orbital, right? So it is in a p orbital which is unhybridized, right? So unhybridized p orbital, that's what we're focusing on in here, right? So unhybridized p orbital, the other carbon over here on which the lone pair is, that is actually sp2 hybridized, right? So just keep that in mind. So the lone pair is in an unhybridized p orbital, so that is just indicating that there's an extra unhybridized p orbital over here. So whenever you see lone pairs, just be careful about that. Just see if it is sp2, then there's probably another p orbital which is unhybridized, right? But if it is sp3, then there's no other unhybridized p orbitals, right? Everything else is hybridized, but only in cases of sp2 hybridization, which you can find out via steric number calculation, and for that you can visit my previous videos to clarify that. So just make sure that you're clear about that, right? So now we have counted out 5 atomic p orbitals, which we can just write over here on the left. And then now we have to focus on the occupancy, right? We just have to focus on electrons, right? So for electrons, we show a pair of electrons like this, right? So over here, this is how we show a pair of electrons, right? So this is what we will do, right? So we just have to now count the number of electrons that are present in these unhybridized p orbitals, right? So each of these unhybridized p orbitals is going to donate like 1 pi electron, right? So this p orbital over here at the start, so over here there's 1 p orbital here, right? So each pi bond is 1 p orbital, so 1 p orbital, so I'm going to be like putting that in red wherever there is a p orbital, right? And each of those p orbitals is going to be donating like a pi electron, except for the middle one, right? So for the middle one, just be careful, right? So there is like a p orbital over there as well, but we already know it has 2 pi electrons over there, right? So we have to count that as 2 because that's the lone pair, but all the others will just give us 1 pi electron. So it is 4 plus 2, that is 6 pi electrons, right? So we're going to be focusing on the number 6. So we have like 6 pi electrons, and we're going to draw it in like this. And yeah, so just focus on like drawing another like pair over here, and we can draw it in like this. So why did I not draw like like a lone pairs over here, right? Why did I have it over here, like in this place and not in this place? Like why would that have been wrong? Because we have a non-bonding orbital right in the middle, right? So we have to focus on drawing that as well. Okay, so we have a non-bonding orbital over here. Why? How do you know when we have a non-bonding orbital? How would you know that? That is the question, right? How would you know? So whenever you have an odd number of the atomic p orbitals, you know you have a non-bonding orbital. If it is even, then you don't have any non-bonding. You only have bonding and anti-bonding, right? So this one over here is bonding. So the middle one is usually non-bonding, and the ones on the lower side are bonding, and the ones on the higher side, they are anti-bonding, because anti-bondings are higher in energy. That's why they are shown as above, right? They are more unstable, right? The electrons would not want to go in them, right? Because that those are higher energy. The electrons always want to occupy lower energy states, right? So just keep that in mind as well. So basically this is what happened, and basically number of nodes is just remember to fill out, like, number of nodes is just like counting, right? So it will basically start from 0, 1, 2, 3, 4. Always start from 0 below and then just count up until the number of, the dashes you have over here, right? That's it. That's like the thing that you have. And basically now we're going to add, like, we're going to now draw out the atomic phases, but remember to draw that out according to the number of nodes. So the phases, which is like the blue shadings you can see over here, so you have to be careful about that, like which part you are shading and which one you aren't, right? So I'll show you how that happens. So in this one, basically these standing infinity things that you see, you just have to make, so the number of these standing infinities that you need to make is equal to the number of atomic p orbitals that you determined, like firsthand. So that was 5, right? So we already have like 2 drawn over here. Let's just draw out 3 more, right? We can just try and space them out as equally as possible. I am not very good at drawing stuff out, so please forgive me for that. I'm trying my best over here. Yeah. Yes, okay. So these are 5 overall, right? So now this is it. So now we will start. So over here at the bottom, if we look, right? So at the bottom, right over here, I'm talking about this this side, just to give you guys an idea of where I'm starting from. I'm starting from the bottom. Okay, so let's start from here. So because there are 0 nodes, that means all of the phases, all of the shadings, they are done on the top or completely on the bottom. But they are all like one phase, right? Either you're completely positive or completely negative. Let's take like above that line positive and below that line negative, right? So they are all right now completely above that line. So let's just take it as that, right? So let's just shade all of that as blue on top, right? And then after that, because there are no nodes over here right now, right? But then after that, when we go on to the second one, we have like 1 node. So always draw like the nodes in the middle, like divide them as equally as possible. So the first node would be in the middle over here where I drew that green. So all of the green dots that I will be drawing out, they are your nodes, right? So just keep that in mind. And now I will, so like before the node, it's blue or on top. Now after the node, the shading is, so how you will be doing the shading, it will be something like this, right? So you will draw it out like this. So over here, basically these 2 will be on top. The first 2 will have their shadings on top, and the last 2 will have their shadings on the bottom, right? And this one, you can just like kind of like see how it goes. Now we'll just focus on like elongating this, because then it's easier to draw that, like those waves over here. So we'll just focus on doing that. And let's say if it starts from here, the node, if it's going from the top, it will go like this, right? So this one, just in the middle one, let it be like this. The other ones, that's why they're shaded at the bottom. So wherever like the node is curving, like so you see this part on, so like it's curving on the top. So that's why the upper parts have been shaded. Now it's curving on the bottom, so now the bottom parts have been shaded, right? And now for the next part, what's happening is that we have two nodes, right? So we'll do something similar. So now we'll have like a node over here and another node over here, right? So this is for the non-bonding now that we're doing it. So we'll have like the wave, which will go ahead like this, and then like this, and then like this, right? So it will start like that. And so now if we go on to the shading, so we'll have some shadings done like that, and another one like that, right? So this is what is going to happen. We can leave the ones where the nodes are like unshaded, right? And now going back to the next one, now we have 3 nodes, right? So for 3 nodes, we're just going to draw the nodes out like that. This does not seem like it's equal, so let's just draw it like this then, right? That is a better one. And let's elongate that. Let's start from over here, and we'll have something like this. Now when we come on to the shading, we'll have something like this, and we'll have something like this. This is how you shade again, right? And now we have 4 nodes, so for that we're going to shade it like the following. So for 4, we're going to have something over here, here, and here. This is how it can be equal, and we're going to try and draw it out. Something like this. And now we're gonna try and draw out the waves, right? So we're gonna start from here. This is how it's going to go on, and now we're gonna shade it in, right? So, and that is how it ends over here, right? So I think we've gotten it all done. We've done the namings, we've gotten the number of nodes and the occupancy and the number of p atomic orbitals down. So now we can focus on doing like the next part of the question, which focuses on like how many atoms are the most stable electrons spread over, right? So before that, you can see like there was already like a set of instructions. You can read through that, but I hope that also the explanations that I gave you while working through this question were also helpful, along with these instructions that were already given by the professor. Yeah, so coming on to this part, which talks about like how many atoms are the most stable electrons spread over. So for this one, and then they ask like, are they more or less stable than the neutral version? So how many atoms? That is a very like targeted question. So how many atoms are the most stable electrons spread over? So if you go back, so it is spread over 5 atoms, right? Because that means it is asking for the continuity, right? So for this, we count the number of adjacent sp2. For this kind of question specifically, we count the number of adjacent sp2 or sp hybridized atoms that have like the unhybridized p orbitals and are basically forming a continuous conjugated chain of, like the unhybridized p orbitals. So in this case, it is 5, right? Because if you start from over here, if you start by looking at this molecule, if we do like the naming, this carbon atom over here is sp2 hybridized. This one over here is also sp2. This is sp2, and this is also sp2, and this is also sp2. The rest, the ending carbons, they are sp3, right? But in continuity, we can only see 5 of them. So the answer for the first part of that question is 5, right? But now it's asking, are they more or less stable than the neutral version? So neutral version is the one which is not an anion, right? Not an anion. So it would have been something like this, right? Without any like charges on it. So this one does not have any resonance, right? There is no resonance. So the less the amount of resonance structures, the less stable it becomes then, right? So it is definitely a lot less stable then, right? How can we say that? Because if you look at part C, right? Part C basically asks you for drawing all the appropriate resonance forms for hepta 2,5-diene 3-ene anion. So if you like look at that part instead, like if you try and draw out the resonance structures for this thing, we have something like this. So the first resonance structure would be just something like this, right? So or actually we should, I believe we should just start from over here actually, right? So let's just try and move this over here, right? This is how it starts. We always move the lone pair first, right? So let's just do that because I've learned a lesson. I've learned from my own experiences to always move the lone pair first and then the pi bond. So we're gonna move the lone pair like that and the pi bond like that to get something like that done. And now after this we're going to we have this, so we can move this over here and this over here, right, to get something like this done, right? We can already see three resonance, right? Three resonance structures, which means that this one, the anion, is definitely much more stable than the neutral form of this molecule.